Out of the pitch-black void of space, a violent burst of extreme ultraviolet light erupting from our local star. It originates from an atmosphere that defies natural logic. Near the visible surface of the sun, the temperature sits at a few thousand degrees, yet moving just a few miles further away from the core causes that temperature to violently spike to over 500,000 degrees. This graph illustrates the standard physical logic we experience on Earth. As distance from a heat source increases, the temperature drops. The sun breaks this rule. Its atmosphere gets exponentially hotter as you move further away from the surface. To understand the mechanics powering this thermal paradox, we have to look past the light reaching our eyes and virtually descend through the layers of the star to find the engine room. The Solar Dynamics Observatory, or SDO, acts as a technological translator, capturing the extreme, non-visible ultraviolet light emitted by the surrounding plasma. The light it reads has made an arduous journey. By the time it escapes the extreme pressure of the sun's core and reaches the lens of the SDO, those photons can be up to 170,000 years old. Our descent begins at the outermost layer of the atmosphere, the corona. Burning between 1 and 20 million Kelvin, its massive, radiant exterior is briefly visible to the naked eye during total solar eclipses. At these blistering temperatures, billions of tons of charged plasma act erratically. Some of it ejections across the solar system, while other material is trapped by magnetic fields, falling back toward the star as superheated rain. While the corona is where this immense heat is expressed, the mechanism generating it lies much deeper down. Dropping just beneath the corona, we hit a narrow boundary known as the transition region. In a star millions of miles wide, this entire layer spans a depth of only 100 kilometers. At the bottom of this shallow slice, the atmosphere sits at a comparatively cool 8,000 Kelvin. At the upper edge of that same 100-kilometer gap, the temperature reaches levels 346 times hotter than fiercely erupting earthly lava. Standard ambient heat radiating outward from the sun's core cannot account for an instantaneous spike this drastic across such a short distance. The transition region exists as a volatile boundary layer, warped by invisible forces rising from the depths below. Plunging another layer down, we enter the chromosphere. Measuring roughly 1,700 kilometers deep, this is the final atmospheric layer before the surface. Here, the landscape is dominated by spicules, massive, densely packed jets of plasma that relentlessly sway and shoot upward from the star's interior. The physical violence of these jets is difficult to comprehend. They tear upward at 100 kilometers per second, 282 times faster than the speed of sound. A single one of these surging spicules reaches a vertical length stretching miles into the sky, dwarfing the absolute peak of Mount Everest. Scientific models long struggled to account for the physics here. Magnetically charged particles should be trapped by the sun's crushing gravity, yet they consistently surge upward to form these massive structures. In 2017, researchers identified a critical interaction involving neutral particles. These uncharged particles slip through the magnetic fields, creating a buoyant force that physically pushes the charged plasma upward. This interaction provides the specific lift needed to feed superheated material into the upper atmosphere, making the massive heat transfer possible. Pushing through the bottom of the spicules, we finally reach the photosphere. Though it appears to have a sharp edge, it lacks a solid surface. At these temperatures, matter exists exclusively as plasma, a churning, violently active sea of ionized atoms and free electrons. This diagram shows a solar granule, a primary mechanism of the surface. These massive convection cells span thousands of kilometers. Superheated fluid boils up from the interior, spreads across the surface to cool, and then sinks back down the dark edges. The plasma flowing within these cells reaches supersonic speeds. This friction generates constant sonic booms, sending physical shock waves rippling across the sun's surface. Occasionally, this boiling convection process is suppressed, leaving cooler, darker patches known as sunspots. Sunspots are areas where intensely powerful, tightly wound magnetic fields trap heat and pressure directly beneath the surface. This bubbling, magnetically trapped layer serves as the engine room driving the atmospheric chaos above. With the mechanics of the surface exposed, we can trace the chain of events back up to the corona. Extreme ultraviolet imagery shows that the violent solar flares erupting millions of miles high occur exactly over the sunspots on the photosphere. As the convection cells boil against the sunspot regions, the trapped magnetic fields twist under the pressure. When they reorganize and snap, they function as a planetary-scale kinetic catapult. That snapping energy drives through the chromosphere, utilizing those neutral particles to whip billions of tons of plasma upward. The extreme heat of the sun's outer layers results from this violent magnetic kinetic energy being aggressively fired from the surface below. From 93 million miles away, the sun appears to the naked eye as a simple, steadily burning disk. The light our eyes can process leaves us blind to the raining plasma, the convective sonic booms, and the violently snapping magnetic fields. Those invisible mechanics have direct consequences here. Solar winds escaping the open coronal holes travel across the solar system, eventually colliding with Earth's protective magnetosphere. That violent, invisible solar kinetic energy is translated into the vibrant, dancing colors of the aurora lights. The universe is teeming with complex activity that occurs entirely outside our narrow visual spectrum. Understanding the cosmos requires developing the technological tools to look closer, uncovering the invisible forces constantly shaping our reality.